dedicated circuit, the translation table here will make a connection from here to here. And this is at the operator. Okay, so they're going to make a connection here to here, and that's how this guy can talk to this guy. Okay, and how do we share the entire copper line? Well, we share by time multiplexing. Okay, so from 0 to from integer n to integer n plus 5 seconds. The first guy is using the line, okay, and then on the second half, the second user is sharing the. Okay, so we time multiplex in this fashion. Okay, so that's one way to accommodate more people. So this is some of the features. Is this certainly with a dedicated line, you can afford to have a constant bit rate. Right? You have a dedicated line, okay? You own the line. So you can do whatever you want to do with it, okay? And it depends on the implementations. You get a certain amount of bit rate. Okay, so for example, a 64 kilobits per second PCM channel, postcode modulation channel. Okay, so this certainly has very short transmission delay. And it doesn't have any small jitter delay. Okay, you own the line, so you just keep on communicating. There's no problem. There's no interruption. Okay, so that is the public switch telephone network of plain old telephone service, and some of the earlier internet connection is based on this technology. For example, ISDN. Okay, now so this is certainly suitable for real-time application that requires constant bandwidth. Okay, for example, you can do audio streaming, not compressed audio, but just raw audio streaming, right? Take directly from the CD, communicate over the line. Okay, you have constant bit rate. Every second you have to send 44,100 samples. Each sample 16 bits, so on and so forth. Okay, and maybe it is also good for something with pretty much constant bit rate compressed video. For example, when we do video conferences, okay, just one camera here, focus on the room. Okay, the bit rate is pretty constant. Right? People are moving, but nobody is moving in a drastic fashion, right? There would be no camera panning. As we see yesterday, panning gives you a lot of bit rate, right? A lot of motion vectors, a lot of residue, right? But if you have a fixed camera and not too many object movements, you are pretty close to constant bit rate. So in some cases for video communications, this is actually okay. Okay, and that's how it's being the earliest teleconferencing package or applications actually just use ISDN. Okay, and there's no problem. The resolution might be low, the quality might be low, but it works. So now, this type of network is certainly not efficient for bursty applications. When you download something, when you transfer something, when you grab web browsing, or with circuit switch, you have the constant bit rate like this. And if your bit rate happens to be moving in this fashion, then you're wasting your bandwidth here, right? Because you don't use up your allowable bandwidth, and you are running into trouble here. That's a problem. Okay. So that's why people are more motivated to design something called packet switching networks. Okay, and this is the type of protocol that we're using every day now over the internet. So it's the end-to-end data stream is divided into small little chunk of data called packets. Okay, and these packets are sent over communication channels. Packets from different users can share the same network resources. That's the entire idea. And each packet will use the full length bandwidth, okay, during the time allocation that is allowed for transmission and receiving. Packet travels through the link through packet switches, or also known as routers. Right? Nodes, intermediate nodes that receive a packet and then send it to another node. Okay, it allows more users to share the networks. Okay, but there are several things that we can get into trouble with this kind of implementation. We need some kind of buffers or queues and require the routers, because there are many people sharing the networks. Many packets from many users can come from to a node simultaneously at roughly the same time. So you need a buffer to store all those packets, and then go into the packet headers to figure out who is sending what packets to who, and who has the priority in retransmission. Okay, we're going to talk about this in a few minutes. If the link is busy, then the packets are queued in the buffer, and if the buffer is full, you have this problem. Packets will be dropped. Okay, if the buffer in a certain router is full, it will not accept any more packets coming in. It will be dropped, and then that leads to packet loss. Okay, so the principle is this. This is a typical data packet. It has a headers. It has what we call payload or the body. This is where your data stays. Okay, and it has a trailer part. Now, what does the header do? The header has the packet length, the overall length of the entire packet, the packet number or the index of the packet. Okay, this is number 2 out of 10 packets that user A is sending to user B. Okay, it's very intuitive, right? So based on the index, the receiver is going to receive all the packets that involves AB. Based on the index, put all the packets together, concatenate them together into a stream, cut out the header, cut out the trailer, concatenate the body together, and you get back your part. Okay, that's how it works. Now, you have source and destination routing information, or IP information. Okay, so when you hit send, okay, then the IP address of your current computers is going to be stored somewhere in the headers, and the IP address of who you want to send it to will also be stored in the headers. Okay. Now, and it also has synchronization and transmission protocol. Okay. We'll talk about this in a few minutes. Okay. The payload is the body which contains the data to be transmitted. Okay. So, and typically there's no fixed rule on how large, how long, or how short the payload will be. Okay, it's packets varies in size. There's a typical size that the computer likes to pick, but as if we implement our multimedia communication system, we have the flexibility. We can make the payload. Well, we shouldn't make it too large, okay, because then protection will be difficult. But it's certainly a lot more flexible. Now, the trailer or the footer right here in yellow is some kind of channel code, some kind of redundancy check codes, parity checking codes on the payload, so that you know that the body is received okay or not. Okay, so that's how your email gets to you without any error whatsoever, because it has a lot of redundancy checks, and if problem arises, okay, then it will request a retransmission. Okay, it will request a retransmission. So if you request enough retransmission, eventually the packets will get there, and everything will be okay. So you can have retransmission requests. Okay, and in our internet protocol, we have retransmission. In some of the multimedia streaming protocol, we don't have retransmission. Why is retransmission bad?
Because it's
delay. It introduced delay. That's the main reason why it's bad. Okay. So some of the features is that your packets have variable length. Okay, it has pretty large transmission delay. There's no warranty. There's no warranty. Okay, the router has somewhat of a random assignment. when it comes to